Ah, it's not melting. It's very disappointing. Yeah, so for a messy problem like this, or sometimes just because I want to give you a quick problem on a test or something, I'll just ask for the first few non-trivial terms to a question, all right? There are two reasons I do that. The one is to make the problem easy and short. The other is because it's something like this, where the full calculation is just onerous. I mean, it's too much. Let me do this. This example is particularly easy because it's one we already know how to solve, but it's also illustrative. So if you don't mind, I know you guys know how to solve this a different way, but let's solve it with series. Y prime prime plus y equals to 0. You guys know the solution to this. You know it's sine and cosine. Let me show you how we can derive that with series. Okay, so we suppose that y is equal to the sum. K equals 0 to infinity of a sub k x to the k. What is it? Is okay? I mean,
yeah.
You guys can ask questions. I mean, it's not like you're gonna inconvenience a significant portion of the class who doesn't understand. I mean, it's okay. Anyway, I know sometimes I have a question that it just doesn't make sense to ask the professor. I just need to talk to the person next to me too, so that's fine. Just saying, don't be afraid to ask questions. I don't mind. Okay, so we're assuming that we have a power series solution. Next, differentiate. Again, I know that you guys know the solution to this already. That's not quite the point here. Differentiate again. All right. Now we plug it in. So this informs us that we want the sum, k equals 2 to infinity, of k times k minus 1, a sub k, x to the power k minus 2, plus the sum, k equals 0 to infinity, a sub k, x to the power k, equal to 0. Now we can't really go forward here until we do some massage, I suppose, on these series. I mean, these are apples and oranges, so to speak. In order to add two series together, you need them to have sort of matching format. All right? So I would suggest that we should change the first series so that it looks a little different. In other words, I'm going to make the first series look like the second series. But rather than making a substitution of the same variable, I find that's confusing. I'll introduce a new variable. I'll say we should let k minus 2 equals to j. All right? Now if I do that, what's that make j equal to? I'm sorry, I'm an idiot. Let me ask a slightly less dumb question. What is k equal to? J plus 2, right? So what's k minus 1 equal to? J plus 1, right? And when k equals to 2, that tells me j equals to what? Right, j equals to 0. Now, it so happens that while these series look different, they actually have all the same orders. For other problems we work, we have to be careful. We may have to throw out a couple of introductory terms on one or the other and make them start at 2 or 3 or something. That doesn't happen here because they both start with constant terms. So we can just, once we make this substitution, we have, in terms of the j variable, this is the sum j equals 0 to infinity of what? J plus 2 times j plus 1. K is j plus 2, x to the j, right? Plus the sum. And now over here, if you don't mind, I'm going to make a different j substitution. It's a very stupid j substitution. It is a substitution. K equals 2j. Okay. So I can rewrite this sum as sum j equals 0 to infinity of a sub j x to the power j. So now you can see that we can combine them, right? Into one big grand glorious series of j plus 2 times j plus 1 times a sub j plus 2 plus a sub j parentheses x to the power j equals to 0. Yep.
So why didn't we replace it with j instead of just rewriting that first one with the summation of k equals 0?
Because I think it's confusing to use k in two different ways. You could be like, I think it's confusing to use j in two different ways. Fine. Maybe I should make the other one n and then call both, I don't know. Anyway, you got to understand this idea. You don't have to do it exactly my way, but we should all agree that we get to the same thing. I mean, if you don't like it with j, we could just as well, in fact, I prefer this, n, 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 n. There you go. Also true. It's a dummy index of summation. You can put whatever you want there as long as you maintain the pattern. Okay, so what does this mean? This means that this has to be 0 for n equals to 0, 1, 2, and so forth. So this actually gives us a recursive relation between the nth and the n plus 2th. N plus 2th. It gives us a recursive relation between the coefficients, all right? So let's look at that. Yes, how do I know that? Can anybody tell Luke why I know that? This is a power series, right? So if you want to, I mean, one way I could look at it, if I plug in 0, right, that gives me the 0th coefficient is 0, right? So then differentiate it. Then the first coefficient becomes the constant coefficient. Plug in 0. You get the first thing is 0. Differentiate it 2 times. Then the second order thing becomes a constant coefficient. When you plug in 0, everything higher goes away. And so forth and so on all the way down. So whenever I have a power series equal to 0, every coefficient in the power series has to be 0. In other words, it works the same as like polynomials. If I have something like, you know, ax squared plus bx plus c equals to 0 for all x, that's the thing, for all x, then a, b, and c are all 0.
So we know that statement goes to 0 because the whole sum is equal to 0.
Right. I mean, if a power series is equal to 0, then for all x, you know, for some range of x at least, some interval of x, it follows that the coefficients are 0. Yeah. Again, you can prove that by plugging in the center, differentiating, plugging the center into the derivative, differentiating again, plugging the center into the second derivative. That will give you level by level by level that the coefficients are 0 in terms of a calculation if you want. But anyway, so we have this. And I would repackage this as an plus 2 is equal to minus 1 over n plus 1 times n plus 2, right, times a sub n. Because it's easier for me to think about it like that. And so you see I can just start down the chain both ways. The one way I would go, a sub 2 is minus 1 over what? 1 times 2 a sub naught. What's a sub 4? A sub 4 is minus 1 over 3 times 4 a sub 2. But by the way, that's minus 1 times minus 1 over 3 times 4 times 2 times 1 a sub naught. Continuing to recurse, a6 minus 1 over 5 times 6 a sub 4, which is, by the way, minus 1 times minus 1 times minus 1 over 6 times 5 times 4 times 3 times 2 times 1. Fine, I'll throw in the 1, a sub naught. At some point, after you do this long enough, you notice a pattern. Right? And if you're a math major, you feel a deep-seated need to prove that the pattern is true by induction. But for you guys, you just notice the pattern and you write down the formula. All right? So like this, I can see the pattern. The pattern is that a sub 2, a sub 2j is equal to minus 1 to the j divided by 2j factorial, all times a sub naught. Those are your even terms. Odd terms. I notice a sub 3 is minus 1 over 2 times 3, a sub 1. Or, if you like, minus 1 over 3 times 2, a sub 1. Then a sub 5, minus 1 over 5 times 4, a sub 3, which is minus 1 times minus 1 over 5 times 4 times 3 times 2. You can throw in a 1 there if you want, but I'll leave it. A sub 1. I mean, this is minus 1 squared a sub 1 over 5 factorial, right? Minus 1 a sub 1 over 3 factorial. A sub 7 minus 1 over 7 times 6 a sub 5, which is minus 1 times minus 1 times minus 1 over 7 times 6 times 5 times 4 times 3 times 2. Minus 1 cubed a sub 1 over, what is it, 7 factorial? Yeah. I may have messed up my sign. Give me a second here. No, that's right. So you hopefully can see the pattern. A sub 2j plus 1 is equal to minus 1 to the j over 2j plus 1 factorial times a sub 1. So then, put it all together. We got what? We got y is equal to, I can pull out the a sub naught, right? And that gives me a sum j equals 0 to infinity of minus 1 to the j over 2j factorial x to the 2j plus a sub 1 parentheses times the sum j equals 0 to infinity minus 1 to the j over 2j plus 1 factorial x to the 2j plus 1. Now, those are exactly the series that I wrote a little bit earlier today as the real and imaginary coefficients of e to the I theta, right? Those are precisely the power series for cosine, right? This is cosine of x, and this here is sine of x. So one way you could look at this is we found another way to derive that sine and cosine are in fact the solutions to y prime prime plus y equal to 0, right? There are a few different ways you could look at this. You could use this, in fact, as a method to define sine and cosine, right? You could say cosine is the solution of y prime prime plus y equals to 0, for which y of 0 is 1. And you could say sine is the solution of y prime prime. So cosine, what is cosine? Definition. Cosine of x is solution of y prime prime plus y equals to 0, for which y of 0 is equal to 0, and y1 rather, and y prime of 0 is equal to 0, and likewise sine of x is, we have y of 0 is equal to 0, and y prime of 0 is equal to 1. You could use these as definitions for sine and cosine, completely divorced from trigonometry, completely born on the theory of power series. And you could use this to define pi in a non-geometric way. You could say that pi is the first, what cosine of what? Cosine of pi over 2 is 0, right? So you could say that's the first 0 of cosine. So you could say the first 2 times the first 0 of cosine is what we call pi. This gives you a definition for pi, completely divorced of geometry just in terms of series. So if you wanted to prove things about pi, you could use this as a starting point. But anyway, I hope you can tell this is a stupidly general method, and we can solve problems we couldn't have even hoped to touch before with this, right? I mean, it's stupidly powerful, but it's also, it's involved, right? Yeah, this is computationally a little bit tougher than what we were doing, I think. Yeah. Thanks, guys.